Welcome, glad you're here, especially if you're interested in low-pass RL filters, because that is going to be the subject today. But if you would like to have a little bit of an intro on inductors, and should probably check out the previous video, which was on high-pass RL filters. So I just kind of gave a little bit of a review and a refresher on how inductors work with respect to time, because that's pretty helpful in understanding how filters work. But in this case, I'm just going to kind of jump right into to the circuit we're looking at without doing that review this time. Also, if you're interested in RC filters that use capacitors instead of inductors, there's a couple of videos I made on those if you'd like to check those out, and I'll just go ahead and tag those here. But if you're here for low-pass RL filters, let's jump in, and I'm going to explain this a bit quicker than I did with the RL high-pass filters, but let's go ahead and get started. So here we have a circuit here. So I've got my voltage source, I've got a resistor, and I've got my inductor at 350 millihenries. And what I'm showing here is a plot. So if I go here, this is like if I just kind of turn this battery on, you can see in the cyan, I'm just turning it up to 5 volts. And what's going to happen is my response across this inductor, as I explained in that previous video, it's going to start off at 5 volts to kind of the EMF is sort of a resistance to changing current that's based on Maxwell's equation. It's going to oppose that with an initial voltage across it, and then that voltage is going to tend towards 0 as this inductor kind of changes from acting like an open circuit initially to acting like a closed circuit, or like a short circuit, or just like a wire eventually when not enough time passes. So you can see sort of the temporal response here. It starts off following at 5 volts, but then it'll trails down to 0. So we can go ahead and run this and just see kind of, and it just kind of sits at 0. At this point, when it's at 0, now that current's sort of like fully passing through here. So that's important. What the voltage is happening across the inductor, especially for the high pass RL filters. But for the low pass RL filters, we're actually interested in what's happening across this resistor up here. Okay, so let me reset this, and let's go ahead and run this and see what's happening. So let me go ahead and pause it here. So we got in the cyan, this is our source, so it's going from 0 to 5, and we recall we looked over here at what's happening to that voltage across the inductor, and it's going from, it's mimicking that source at 5 volts, and it's trailing off to 0, and just holding there at 0. So what's happening across this resistor, you could think about it when the voltage across this inductor goes to 0, because that inductor is becoming like a short circuit. Well, then, based on Kirchhoff's voltage law, as the voltage across that inductor goes to 0, the voltage across this 187 ohm resistor has to go to 5 to balance out that battery. So you could kind of think of that, it's got to kind of be the opposite to balance it out. Okay, so let's go ahead and take a look now at what happens when instead of this DC voltage, we have an AC voltage at 20 hertz square wave. So here it is. I'm going to go ahead and run it, and you'll see the same thing happen initially when it goes up to 5, and then it's going to go down to -5. So when it goes down to -5, this is a little bit tricky. So this voltage across my inductor is actually going to go down. It's going to shift by 10 volts, because the voltage across the source shifted by 10 volts. So it's going to shift corresponding, it's going to go from 0 to -10, that same 10 volt swing. So as it does that, the voltage across the 170 ohm resistor is going to kind of counterbalance that. So KVL's the equation works, and so that it all sums up to -5. So this is going to start off at where it was, which was at 5, and it's going to drop down eventually to -5, where you see it over here. So this is the response at 20 hertz. So you can see in general, as the voltage across my inductor is trending towards 0 either way, then the voltage across my resistor is going to tend to match. When its sufficient time has passed, it's going to tend to match whatever the voltage is across our source. But if you look at the duty cycle here, you could see that for the most of this like whole 25 milliseconds across here, we have that voltage across my resistor is going to match that voltage across my capacitor. So you could say that it is, if I took the voltage across this resistor as my output voltage, which we do for low pass RL filters, then at 20 hertz it looks like it's going to be passing that signal, because it's following that source signal for most of the duty cycle. But let's just go ahead and check out what happens if we ratchet up this frequency a little bit. So let's go ahead and crank that up to 85. And before we do that, let's go ahead and get rid of this voltage across our inductor, because we're really, for this low pass RL filter, we're just interested in that voltage across our resistor. And of course I'm looking at 85 here because that's going to be our cutoff frequency, which is the same calculation as it is for the high pass RL filter. So let's go ahead and reset this and run it. And you can see this is like a little bit more interesting because like the voltage across here is trying to match that source, but by the time it gets close to matching it, it switches again, and then it kind of tries to match it, and then it gets switched again, and then it almost gets to matching it, and then it switches. So this is what's happening when you're at that cutoff frequency. It's kind of like it's not really it doesn't have enough time to really follow it well, but it's also not that bad of attenuation. So this is our cutoff frequency. So let's go ahead and crank this up to 1 kilohertz and see what happens there. Okay, so at 1 kilohertz you can see that the voltage across my resistor here is sort of trying to follow the voltage across my source, but it just doesn't have enough time. Like it's not quick enough. It's not responding quick enough, so it just kind of goes up and down slightly, but it's not really following it. So you could say this is like a highly attenuated replication of what that signal is across here. So this wouldn't really be passing, it'd be more rejecting what that voltage is across our source here. So in order to kind of compare these, let's take a look at a frequency response graph where we can kind of see where each of these fit. Okay, so this is my frequency response graph, and just to kind of make sure you're understanding where we're at here, on this x-axis we have our frequency. So like say here this is at 20 hertz, and if we go up to here this is like 200 hertz, and it's on a log scale. And on the y-axis we have the dB of attenuation. So if you're up here, you see like if you're at this line on the y-axis, it's like you're not really attenuating at all. It's totally passing it. But as you go further down this y-axis, that means we're getting more and more attenuation. So if we start off going out to our 1 kilohertz, we see that this is what we last looked at, and we have a pretty significant attenuation. It's at negative 21 dB. So this is like we showed in that plot, like it's not really tracking that input signal. It's just kind of barely doing it. So it's getting significantly attenuated at 21 or minus 21 dB. So not passing it at this point. So it could be rejecting it. If we go back to 85 hertz in this area somewhere, you see that we've got around negative 3 dB, and that's because this cutoff frequency was at around 85 hertz. So we're seeing that it's kind of passing it, kind of not. Probably not the best range to operate a filter like this because it's not really probably doing what you want it to do. But if we go back to say 20 hertz, then you can see this is actually doing pretty well. We have a attenuation of only negative 0.23 dB. So, and for the most part, it's really passing that whole signal at this point. So this would why we call it a low pass signal, because it's going to pass at 20 hertz with low attenuation, low dB here, but it's going to cut it off or reject at say 1 kilohertz or higher. And again, the sort of the rationale behind it is that voltage across that resistor, it tends to want to follow what that source is, but it needs enough time to get there. So if you keep oscillating so fast, it doesn't really have a chance to keep up, and so it won't really track what that input signal is. But in general, I hope this kind of explains how a low-pass RL filter works. And the only difference between the high-pass RL filter and the low-pass one is for the high-pass one, I'm putting my output voltage across the inductor, and for the low-pass one, I'm putting it across the resistor, and they kind of act reciprocally, because if my voltage across my inductor is following my voltage source, then by definition the voltage across my resistor can't. Because because KVL, it's kind of got to be the opposite, and vice versa. So that's how an RL low pass filter works. And if you're interested again in how a high pass RL filter works, there's a video on that. Or if you're interested in RC low and high pass filters, you're definitely welcome to check those out. But if you're interested in RL low pass filters, then I hope this was helpful. And until next time, take care.